Today I will be discussing the process of a Wittig reaction. This reaction converts ketones and aldehydes into alkenes using the Wittig reagent. Before we discuss the Wittig reaction in depth, we first need to understand how the useful Wittig reagent is synthesized. The first step in the Wittig reagent synthesis is an SN2 reaction between an alkyl halide and triphenylphosphine. In this case, 2-bromopropane is our alkyl halide containing the bromine leaving group, and triphenylphosphine is the nucleophile. The lone pair of electrons on the phosphorus atom of triphenylphosphine will attack the partial positive carbon. This will allow bromine to take the remaining electrons and act as the leaving group. The second step is a proton transfer. Now that the phosphorus and carbon atoms are bonded together, phosphorus holds a positive charge. A strong base is needed to deprotonate the carbon atom, such as butyl lithium, which is shown here. In this case, lithium is the spectator ion, leaving the negatively charged carbon chain acting as the base. The lone pair on the base will attack the hydrogen, giving carbon a lone pair and a negative charge, which is stabilized by the positive charge on phosphorus. Now we are left with our Wittig reagent, a phosphonium ylide. The negatively charged carbon allows it to be highly nucleophilic and react well with ketones and aldehydes. To understand why the Wittig reagent is so stable as an ylide, we need to look at its other resonance form. The lone pair on the carbon resonates to form a double bond between the carbon and phosphorus. Normally, the uncharged resonance form would be stronger and more stable. In this case, it is not because the carbon-phosphorus pi bond requires interaction of electrons from the second shell of the carbon atom and the third shell of the phosphorus atom. Therefore, the ylide is more stable. Now that we understand how to synthesize the Wittig reagent, we can put it to use in the Wittig reaction. The first step of the Wittig reaction is nucleophilic addition. To reiterate, the Wittig reaction will convert a ketone or an aldehyde to an alkene. In this example, an aldehyde is used. To understand why nucleophilic addition occurs here, we need to identify resonance in the aldehyde. The electrons in the carbon-oxygen double bond resonate to the oxygen atom. This gives oxygen a negative charge, and more importantly, it gives carbon a positive charge. Resonance shows that carbon holds a positive charge at least part of the time, which attracts nucleophiles to attack. Now back to nucleophilic addition, where the Wittig reagent will act as the nucleophile. The highly nucleophilic carbon of the Wittig reagent attacks the electron-poor carbonyl carbon from the front and the back. This breaks the carbon-oxygen double bond, giving oxygen another lone pair and a negative charge. The second step is coordination. The first step, nucleophilic addition, synthesized a betaene. A betaene is characterized by a positive and negative charge, separated by two uncharged atoms, as shown here. The negative oxygen attacks the positive phosphorus due to intramolecular attraction. This will form what is known as an oxaphosphetane. The final step of the Wittig reaction is elimination. The previous step, coordination, formed an oxaphosphetane, which is shown here. An oxaphosphetane is a four-membered ring consisting of two carbon atoms, one phosphorus atom, and one oxygen atom. The oxaphosphetane ring is highly strained, therefore the ring falls apart. As the ring falls apart, the triphenylphosphine oxide byproduct is discarded and we are left with the alkene product. Both E and Z isomers are formed, which in this case are identical. Once the alkene is formed, the reaction is complete.